Spoon, spoon in my hand, who's the fairest in all the land? Why, you, of course, and welcome. Today we'll be talking about mirrors, both convex and concave mirrors. So get out your spoons and we'll be doing a few measurements and seeing whether or not the mirror equation really does work for the types of mirrors that we'll be working with today. And simple mirror for us that should both have the convex and concave mirror would be a simple spoon. And here I have already drawn out is a representation of the mirrors that we'll be working with. Just as an example here, I have a concave mirror that we'll be working with today to just kind of show the example of how to work with a mirror in geometric optics and how the image is formed, particularly from working with geometric optics in that sense. The specific equation I mentioned before is this equation here, and you also notice that I wrote up here the thin lens equation in addition to the fact that this is the mirror equation. They are both, in fact, the same equation, and though they'll be treated slightly different between mirrors and lenses, but for today, we'll be exclusively talking about mirrors only. So keep that in mind. So from our diagram here, we see that our mirror is represented by this curvature here. Our object will just be represented by an upright arrow at some location along the optic axis that we've drawn just straight through our diagram. In addition to everything that we see here, we see that there are the rays of light, which indicate that we are working in a interpretation of light acting as rays and therefore geometrically being manipulated by certain objects, in our case, a mirror. Through these drawn rays that we create, an image will form based on the reflected rays in the mirror itself. Okay, we'll get to that in just a moment. First, we'll need to define a few things. The first thing and most important thing about every mirror is every mirror has a focal length, which is represented by the distance between the focal point and the mirror or lens, if you're working with a lens itself. So that's the distance between those 2 points. So I didn't quite draw this on here. Typically, it's assumed that in the diagram that the focal length is just that distance indicated as such. For convex mirror has a negative focal length. That would mean that the focal point would be behind the mirror and not in front. In our example, we're working with a concave mirror, and that will, by definition, have a positive focal length. All right, so just to kind of keep this in some sort of mnemonic type sense, or to sort of save these to memory in a more easy fashion, just think of the fact that this mirror is producing a cavity or cave-in type structure, and therefore can be considered a concave mirror. Similarly with the lenses as well, concave lenses will have also the same sort of cave-in feature as well. Convex will just be a deflection outward. Also note that any planar mirrors will essentially have focal point or focal length at infinity or negative infinity. Doesn't really matter. But these, an example of this would be something in your bathroom mirror or something you might find in the restroom to kind of groom yourself and all that sort of stuff before you leave. Right? So these are flat or planar mirrors. They're not very interesting for our case today, particularly the concave or convex mirrors, as these don't really distort the image, as we'll see in just a moment. The next thing to also define here is the distance to the object. Again, every distance or length will be measured from the mirror itself and only the mirror or the center of the lens if you're working with the thin lens equation in that particular instance. All right, so the distance to the object is simply the distance from the mirror to the object itself. And here I've drawn the distance indicated as such from the base of the object to the mirror. By definition, the object is always considered in front of the mirror for a single mirror, and therefore will have a positive distance, and therefore just will simply be positive anytime you use this particular equation for a single mirror. Now, depending on what information you might be given, if you're given the focal length and the distance to the object, you may have to try and find the distance to the image. You may be given the distance to the image and the distance to the object, and you may have to find the focal length as well. There are many multiple ways in which this problem can present itself in physics problems. Just be aware that this isn't necessarily the succession of things that you would have to find or be given in your problem itself. So just be aware of that. Now, with the distance to the image itself, if the distance to the image is positive, meaning that the image is on the same side as where the object is located, this image would be considered real. All right, and again, it's in front of the mirror, if that is the case. So we would say that the image is real if the image is located at this particular point somewhere in front. If the distance to the image is behind the mirror or negative, then the image is imaginary. So in our example here, the image is behind our mirror located here. We see that it is imaginary for us. All right, so hopefully what you'll see is that the image is formed by these back traces of the reflected rays that are reflected off the mirror itself. Typically, you only need only 2 rays in order to determine where the image is formed and the height of that image itself. Here, just for completeness, I did all 3. You can always do more if you want to, but these are the easiest of the infinite amount of rays that you can draw in geometric optics. So starting with the first one is that a ray of light emanates from the object perpendicular to the optic axis and then is reflected off the mirror, and its reflected ray goes through the focal point of the mirror itself. The second ray, generally treated as one of the easiest rays to remember, starts at the object. It then goes towards the mirror, towards the center, where the optic axis meets the mirror itself, and then reflects again at the same angle as all these rays will do, and we'll talk about that in a moment. It will reflect at the same angle off that optic axis and will proceed in this direction here. All right. The third and final of the rays that we typically use is that there is a ray on this object that will emanate from the tip of the object and either go from the focal point or look as though it is emanating from the focal point itself, or go towards the focal point and then reflect off the mirror, and that reflected ray will be parallel to the optic axis indicated here. Note that when you guys talk about mirrors, the law of reflection is always discussed in terms of mirrors. The law of reflection just states that a ray of light incident upon a mirror will be reflected at the same angle as its incident angle, right? Its incident angle is given as the normal, the angle that is formed by the ray and the normal to the surface of the mirror itself. So if we bisect all of these angles that are formed by the incident ray and the reflected ray, we will find that the line that bisects these angles will always be normal to the surface of the mirror. Just as a reminder, the normal is the perpendicular direction to the tangent of the surface itself. So the tangent, again, is essentially the line that is parallel to the surface at a given point along that surface itself. All right, and so that makes a normal with each of these, and therefore the law of reflection is being obeyed at every point, though it is most used and most recognized with this particular ray that's drawn, because it requires that use, that explicit use of the law of reflection there. Now, you'll notice that all these rays in this particular configuration of the object in relation to the mirror has these rays all not converging at a single point. So if you find that the reflected, or in the case of lenses, refracted rays do not seem to converge at a single point, what you would then need to realize is that you'll need to backtrace these rays in a particular direction, either one way or another. In our case, for the mirror, it would have to go behind the mirror in order for us to find a convergent point where the image would be formed. Okay, and then once you find that convergent point, again, minimally, you would only need 2 rays. Again, I did 3 for completeness, and sometimes doing 3 helps with making sure that you're not fooling yourself in terms of the rays that you're producing, as well as not assuming that if there's a cross somewhere, like say here, that your image isn't going to be produced there. Okay, just note that this crossing here of 2 rays is an incident ray crossing a reflected ray, which is not where an image should be formed. It should always be where 2 reflected or refracted rays will converge. All right, so just be aware of that. All right, so with that definition, the next thing that I also need to note in terms of mirrors specifically is what is called the radius of curvature. The radius of curvature is something that is both indicative of lenses and mirrors, but for mirrors, they have a very specific relationship to the focal point itself. And you'll notice that here I've written out that the radius of curvature is equal to twice the focal length of the mirror in this given example. You can write it as the focal length is just 1/2 the radius of curvature. Okay, note that this is only for mirrors and not for lenses. Okay, so this is very specific for mirrors themselves. Next thing that you'll also notice here off to the side, I also wrote the definitions of the heights of the image and the height of the object. The heights will be given as the value or the length from the optic axis to the tip of the image or the object itself. Okay, so here I've just drawn dashed line to indicate that this is a continuation of where the height of the object is located and defined it here. Okay, these will be particularly useful for when we talk about magnification of the image that's produced by a mirror or a lens. All right, so moving on with the magnification. The magnification is given as this equation here. Note that there is a minus sign when we use the magnification in relation to the distance to the image over the distance of the object. This again will be true for both lenses and mirrors. Here, for the heights ratio, to find magnification, it's simply the height of the image over the height of the object. Here, again, I define just as above with the focal points, focal lengths and distances. The height for the object is by definition a positive value for a single lens or mirror, since typically the object is always considered upright or sometimes called erect in some cases. They're interchangeable in the case of geometric optics. It's just a preference on how you want to describe those images or objects. For the height of the image, if you have a positive height, the image is considered upright or erect. If the image height is negative, basically it just means that the height or the image is essentially below the optic axis. If we look up above here, if this object or this image was instead drawn in that direction, this would be a negative height for the image itself. Right? That just means the image would be inverted. You'll find a relationship between both imaginary, real, and inverted and upright images that typically your real images will be inverted. And this is the case for both lenses and mirrors, and that your imaginary images will always be upright for a single lens or mirror. Okay, so there'll be a correlation between those two descriptors for when you have to describe the image that's formed by those objects. All right, so with our spoon, we can then go about trying to figure out some specific quantities related to our spoon itself. So what we can do is I've already taken the liberty, and you can watch the video on how I derive this particular equation here, where we find the radius of curvature related to the depth of the spoon, and the chord of the spoon itself, basically the width or maximal width of the spoon in either of its two preferred axes. All right, so here I define them, and just as a reminder, what we'll do, even though that most spoons themselves aren't quite elliptical themselves, we'll just assume that they are specifically a perfect ellipse of some semi-major axis and some semi-minor axis widths themselves. So it depends on how you want to view the mirror itself. If you want to hold the mirror like this, you would then use the semi-major axis as your chord. If you're going to hold the spoon like this, you would then want to use the semi-minor axis of the spoon in order to find that radius of curvature. Okay. Once you find the radius of curvature, you can then find the focal length of the spoon itself, again, by using this relationship we have up here. As an example, I'll just kind of show this with the example that I've written above here. So I've taken the liberty of already measuring the focal length, and that was given as 2.3 centimeters from a radius curvature of about 4.6 centimeters. So again, it's just half radius of curvature. Measuring the distance to the object from here to here, this was 0.8 centimeters. And then the height of the object itself was positive 1 centimeter. So this was just a centimeter in height. So typically when we work with a mirror or lens in a physics problem, we're usually asked 2 questions or maybe just 1 question in that case. Given that that we have the focal length and the distance to the object itself, we may want to determine what the distance to the image is. So when we work with the mirror or thin lens equation, I typically try not to explicitly put any minus signs into the equation itself that are related from the definition itself. I just let the algebra itself of what we're trying to find do the work itself, and then once I've done the correct algebra in order to isolate the variable I'm trying to find, I then plug in to the equation those quantities that were given with either their positive or negative signs themselves, so that I don't have to worry about something going wrong. Okay, so here I went through the algebra of finding a common denominator and then inverting it in that way, since it's much easier to work in this fashion than trying to use an inverse of some inverse of this, where you might be tempted to do it in that particular manner there. It's fine, it works okay. I just like a more simplified equation to work with. Plus, it also kind of helps with ensuring that your unit analysis comes out okay in the end. All right, so plugging in those values, I get a theoretical value of minus 1.22 centimeters away or behind the mirror itself. Now, an important thing about geometric optics is that if you were to draw and measure properly the objects and the focal length, and all that sort of stuff, you can actually use the result that you get from your geometric analysis, all that drawing and all that fun stuff by using protractors and straight edges and all that sort of stuff. You can actually get a value that is roughly similar or very precise in terms of being exactly the value you are looking for. So geometric optics works because not only the algebra gives us a value, but the geometry gives it a very similar, if not the same value out of that. Okay, so it's a very powerful tool if you are to use a straight edge and compass in that method. The next thing maybe asked in that sense is, what is the height of the image using your magnification? Since we just found the distance to the image and we know what the distance to the object and the height of the object is, we can then use this relationship of the magnification, since these are equal to each other, to then determine the height of the image. And we find through algebra and the values that we obtained earlier that we get about 1.5 centimeters. And if we go and measure that using a ruler, we find that we get approximately the same at about 1.4. Note that these differences that I find from the algebra versus the actual measured quantities can come from quite a few different things. Notice here that I'm only going to the first decimal place in my measurements. If I were to do a little bit more precise measuring there, I may find that this gets a little bit closer to what I measure here. There is also the fact that you may not necessarily have drawn things to correct proportions and that you drew everything square enough in the overall diagram. So there's a bit of error involved with the drawing process as well as the measuring process when you go to get these quantities from the actual problem itself. So just be aware of that. Lastly, you can then figure out what the magnification is, and in this case, this mirror blows up the image, or the object, I should say, by 1.5 times its original size. And if we go back to the diagram here, we see that the object is of this height and the image is of this height, indicating that there is an enlargement of that image that's produced in this particular setup. So this is why, for example, if you go and look at makeup mirrors or compact mirrors, these will have a very, very, very large radius of curvature, so that when you put these in front of your face is enlarged and also upright, so that you can do finer details on your face for makeup applications. So that's an application of using a concave mirror in daily life for that matter. So I hope you enjoyed this. Again, if you're interested in the derivation of the radius of curvature, I do a few types of derivations in there in order to validate the equation that I'm using here in a more advanced fashion. So please take a look at that and have fun with your mirrors as you try and figure out what the size of maybe your face is in your magical mirror spoon. So have a good day and stay safe.